As you read these words, wherever you are, perhaps a cozy armchair bathed in the glow of a reading lamp, or a bustling cafe with the clatter of cups, or even a quiet library where only the turning of pages breaks the silence you are experiencing. Time. You are moving through it, consciously or unconsciously, just as you moved through the minutes and hours that led you to this very moment. But what is this elusive, relentless, and utterly fundamental phenomenon we call time? It's a question that has captivated philosophers, physicists, and poets for millennia. Is it a river flowing ever onward? A dimension like height or width? An illusion, a construct of our minds? Or something far more profound and intricate than we can even begin to grasp? Today, we embark on a journey, not through a fantastical landscape, but through the landscape of scientific inquiry, philosophical debate, and the very fabric of reality itself. This won't be a rapid-fire documentary, nor a dramatic narrative with scene breaks and voiceovers. Instead, we will explore, slowly and deliberately, with the patient curiosity of a scientific observer, the multifaceted nature of time, drawing upon the insights of those who have dedicated their lives to unraveling its mysteries. We'll delve into the foundational concepts, the groundbreaking theories, and the perplexing paradoxes, all with a touch of the wonder and even the occasional chuckle that such a grand pursuit inevitably evokes. So, settle in, perhaps with a beverage of your choice, and prepare to ponder, what is time, really? The perception of time, a human construct. Let's begin not with the cosmos, but with our own experience. We feel time passing. We remember the past, live in the present, and anticipate the future. This linear progression seems undeniable. But how much of this perception is an objective reality, and how much is a product of our biological and neurological machinery? Consider the subjective nature of time. A thrilling hour might fly by in what feels like minutes, while a tedious minute can stretch into an eternity. This phenomenon, often attributed to the brain's processing of information and emotional engagement, highlights that our internal clock is not always in sync with the ticking hands of a physical timepiece. When we are deeply engrossed in an activity, our brains process more information per unit of objective time, making that period feel shorter. Conversely, in moments of boredom or fear, the brain is starved of novel stimuli, and each second can feel agonizingly long. Neuroscientists have identified various brain regions involved in time perception, including the cerebellum, basal ganglia, and the prefrontal cortex. The brain doesn't have a single timekeeping organ, but rather a distributed network of circuits that integrate sensory information, memory, and attention to construct our sense of duration. This complexity suggests that our subjective experience of time is a highly sophisticated, if somewhat pliable, neurological construct. It's almost as if our brains are constantly editing a movie of our lives, sometimes fast-forwarding, sometimes lingering on a frame. Moreover, our perception of time is deeply influenced by memory. We perceive events as being in the past because we recall them. We anticipate the future because we can project our minds forward based on past experiences and learned patterns. Without memory, would time even exist for us in the same way? Imagine a being with no capacity for memory. For such a being, every moment would be a perpetual present, devoid of context from what came before or anticipation of what might come next. The concept of change, a fundamental aspect of time, would be meaningless. This thought experiment underscores the profound link between our cognitive abilities and our temporal awareness. Even language shapes our understanding of time. Different cultures express temporal concepts in diverse ways, which can subtly influence how individuals within those cultures perceive and interact with time. Some languages have no future tense, for instance, which might lead to a different psychological relationship with future planning and past reflection. This isn't to say that time itself is merely a linguistic construct, but rather that our articulation and conceptualization of it are certainly molded by the tools of our communication. So, while we might feel time as an external, objective force, our initial foray reveals that our personal experience of it is anything but simple. It's a complex interplay of neurology, psychology, and even culture. This raises a crucial question. If our perception is so variable, what then is the underlying reality? Time as a dimension, Newton's absolute framework for centuries. The dominant view of time was that articulated by Sir Isaac Newton in his Principia Mathematica. Newton posited the existence of absolute, true, and mathematical time, which of itself, and from its own nature, flows equably without relation to anything external. For Newton, time was a universal, unchanging backdrop against which all events unfolded. It was like a giant, invisible clock ticking away uniformly for everyone, everywhere, independent of any observer or physical process. Imagine a vast, empty stage. Newton's absolute time is the unseen, unwavering rhythm of that stage, regardless of whether actors are performing or the lights are on. It's a fundamental container for existence, separate from the events that occur within it. This concept of absolute time was deeply intuitive and aligned with everyday experience. When we synchronize our watches, we implicitly assume a shared universal time. When we speak of events happening simultaneously across great distances, we are invoking this Newtonian notion. Newton's universe was a deterministic one, governed by precise laws of motion. In this framework, knowing the initial conditions of a system and the forces acting upon it would allow one to predict its future state with absolute certainty. Time, in this context, was the parameter that allowed for this unfolding of events. It was the T in every equation of motion. This absolute view of time also implied an absolute simultaneity. If two events occurred at the same absolute time, they were simultaneous, regardless of where they happened in the universe or who was observing them. This seems self-evident to our common sense. If a clock in London strikes noon and a clock in New York strikes noon, they are happening at the same absolute moment. Newton's model provided a powerful and successful framework for understanding the universe for over 2 centuries. It allowed for remarkable advancements in astronomy, mechanics, and engineering. The celestial mechanics that predicted planetary orbits and the trajectories of projectiles were built upon this foundation of absolute time and space. It was a testament to the power of a clear, albeit eventually incomplete, theoretical framework. However, even within Newton's own time, there were subtle philosophical debates about the nature of absolute space and time. Gottfried Wilhelm Leibniz, a contemporary of Newton, argued for a relational view of space and time. For Leibniz, space was not a container, but rather a system of relations between objects, and time was a system of relations between events. In other words, if there were no objects or events, there would be no space or time. This was a significant departure from Newton's absolute container. While Leibniz's arguments were intriguing, Newton's empirically successful framework largely held sway. The universe, it seemed, was a grand machine, and time was its steady, unchanging pulse. This elegant simplicity, however, would eventually be challenged by a series of revolutionary ideas that would fundamentally alter our understanding of not just time, but the very fabric of reality itself. The stage was set for a dramatic revaluation, a revaluation sparked by the very nature of light. The speed of light and the seeds of relativity, the first crack in Newton's absolute framework, began to appear with the study of light. For centuries, light's nature was a subject of intense debate. Was it a stream of particles, as Newton himself believed, or was it a wave like sound? The work of James Clerk Maxwell in the mid-19th century provided a stunning synthesis. Maxwell's equations unified electricity and magnetism, demonstrating that light was an electromagnetic wave propagating through space at a constant speed. This constant speed was the crucial insight. Maxwell's equations predicted that the speed of light in a vacuum, denoted as c, would always be the same, regardless of the motion of the source or the observer. This was incredibly counterintuitive. Imagine throwing a ball from a moving train. Speed would be the speed of your throw plus the speed of the train. But light didn't behave that way. If you shined a flashlight from a spaceship moving at tremendous speed, the light would still travel at c relative to an observer on Earth, even though it was emitted from a moving source. This constancy of the speed of light presented a profound puzzle for the Newtonian framework. If the speed of light was absolute, then something else had to give. Either Newton's laws of motion, which relied on relative velocities, were incomplete, or the very nature of space and time had to be reevaluated. Enter Albert Einstein, a young patent clerk with a penchant for radical thought experiments. In 1905, Einstein published his groundbreaking paper on the electrodynamics of moving bodies, which we now know as the theory of special relativity. Einstein didn't try to tinker with Maxwell's equations. He embraced the constancy of the speed of light as a fundamental principle, and from this single, audacious postulate, he deduced astonishing consequences for space and time. Special relativity. Time is relativity. Special relativity postulates two fundamental principles. The principle of relativity, the laws of physics, are the same for all observers in uniform motion, i.e., not accelerating. This means there's no preferred rest frame in the universe. Your physics experiments will yield the same results whether you conduct them on a stationary Earth or in a spaceship moving at a constant velocity. The principle of the constancy of the speed of light. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source. From these two seemingly simple principles, mind-bending conclusions emerge. The most significant for our discussion is the relativity of simultaneity. If the speed of light is constant for all observers, then two events that appear simultaneous to one observer might not appear simultaneous to another observer who is in relative motion Imagine a train moving past a platform at the exact moment. The middle of the train aligns with the middle of the platform. Two lightning bolts strike, one at the front of the train and one at the back of the train. To an observer standing on the platform, precisely in the middle, the light from both strikes reaches them at the same time. So they conclude the strikes were simultaneous. However, for an observer standing in the middle of the moving train, the situation is different. As the light from the front of the train travels towards them, they are moving towards that incoming light. As the light from the back of the train travels towards them, they are moving away from that incoming light. Because the speed of light is constant, the light from the front of the train will reach the observer on the train before the light from the back of the train. Therefore, the observer on the train will conclude that the lightning strike at the front of the train occurred before the strike at the back. This is not an illusion or an optical trick. It is a fundamental consequence of the structure of spacetime. Simultaneity is not absolute. It is relative to the observer's frame of reference. This alone shattered Newton's absolute time. There is no universal now. My now might be different from your now if we are moving relative to each other. Another profound consequence of special relativity is time dilation. This phenomenon dictates that a moving clock runs slower than a stationary clock, as measured by a stationary observer. The faster an object moves, the slower time passes for that object relative to a stationary observer. Consider two identical twins. One twin stays on Earth, while the other embarks on a long journey in a high-speed spaceship. When the traveling twin returns, they will be younger than their earthbound sibling. This isn't science fiction, it's a proven reality. Atomic clocks flown on airplanes have been shown to run slightly slower than identical clocks on the ground. This effect is minuscule at everyday speeds, but it becomes significant as speeds approach the speed of light. The mathematical formulation for time dilation is given by delta t equals gamma, delta t equals 1c2v2 delta t, where delta t is the time interval measured by the observer in a different reference frame. For example, the twin on Earth. Delta t is the proper time, the time interval measured by an observer at rest relative to the events. For example, the traveling twin (v) is the relative velocity between the two observers. C is the speed of light. Gamma is the Lorentz factor, always greater than or equal to 1. As v approaches c, the denominator approaches 0, and gamma approaches infinity, meaning time dilation becomes extreme. If an object could reach the speed of light, time would effectively stop for it. The third key consequence is length contraction. Similar to time, distances also become relative of its motion to a stationary observer. This is also described by the Lorentz factor. These effects demonstrate that space and time are not independent entities, as Newton believed, but are intrinsically linked. Einstein famously introduced the concept of spacetime, a four-dimensional manifold where the three dimensions of space are interwoven with the one dimension of time. Events occur at specific points in spacetime, and the distance between these points is not just spatial, but spatiotemporal. Special relativity revolutionized our understanding of time from an absolute, universal flow to a flexible, observer-dependent dimension that is inextricably intertwined with space. It painted a picture of a dynamic universe where motion affects the very fabric of reality. But special relativity only dealt with observers in uniform motion. What about acceleration? And, more importantly, what about gravity? General relativity. Gravity and the curvature of spacetime. Einstein wasn't content with special relativity. He knew it didn't account for gravity, the most pervasive force in the universe. Newton had described gravity as an instantaneous force acting between masses across empty space. But how could this instantaneous action be reconciled with the finite speed of light? If gravity propagated instantaneously, it would violate special relativity's speed limit. It took Einstein another decade of intense intellectual struggle to formulate his theory of general relativity, one of the greatest intellectual achievements in human history. Fundamentally reconceptualized gravity, not as a force, but as a manifestation of the curvature of spacetime. Imagine spacetime as a stretched rubber sheet. If you place a bowling ball on the sheet, it creates a dip. A marble rolled nearby will curve inward towards the bowling ball. Not because the bowling ball is pulling it, but because the sheet itself is curved. In general relativity, massive objects like planets and stars warp the fabric of spacetime around them. What we perceive as gravity is simply objects following the shortest path, a geodesic, through this curved spacetime. The profound implication for time is that gravity affects the passage of time. This is known as gravitational time dilation. Clocks run slower in stronger gravitational fields. The closer you are to a massive object, the slower time passes for you. Consider a clock at the top of a skyscraper and an identical clock at its base. The clock at the base is in a slightly stronger gravitational field than the clock at the top. Therefore, the clock at the base will run infinitesimally slower than the clock at the top. This effect is incredibly small in Earth's gravity, but it's measurable. Highly precise atomic clocks have confirmed this prediction. For instance, clocks on Earth run slower than clocks on GPS satellites, which are in weaker gravitational fields. This gravitational time dilation, along with relativistic time dilation, must be accounted for in GPS systems to ensure their accuracy. Without these relativistic corrections, your GPS navigation would be off by several kilometers a day. The famous thought experiment known as the twin paradox, which we briefly touched upon with time dilation, finds its full explanation in general relativity. While special relativity can explain why the traveling twin ages less, it doesn't fully address the asymmetry from the perspective of the traveling twin. General relativity explains that the acceleration experienced by the traveling twin during turnaround when they reverse direction causes the asymmetry. Acceleration is equivalent to gravity. This is the equivalence principle, another cornerstone of general relativity, and therefore the accelerating twin experiences a period of stronger effective gravity that contributes to their slower aging. The concept of a light cone becomes crucial in general relativity. For any event in spacetime, there's a light cone that defines the region of spacetime that can be influenced by that event, the future light cone, and the region from which light could have reached that event, the past light cone. The sides of the light cone represent the paths of light rays. Inside the future light cone are all the events that can be causally affected by the event. Inside the past light cone are all the events that could have causally affected the event. This concept beautifully illustrates the causal structure of spacetime, showing how information and influence propagate at or below the speed of light. At extreme gravitational fields, such as those near black holes, time dilation becomes dramatic. Near the event horizon of a black hole, time effectively grinds to a halt for an outside observer. If you were to watch someone fall into a black hole, you would see them appear to slow down and freeze at the event horizon, their light becoming redshifted until it fades from view. For the person falling in, however, time would continue normally as they crossed the event horizon, though they would rapidly approach the singularity. General relativity profoundly changed our view of time, from a fixed background to a dynamic component of spacetime influenced by the distribution of mass and energy. It means that the universe isn't simply operating in time, but that time itself is an active participant, bending and stretching in response to gravity. It's a truly mind-boggling concept, transforming our understanding of the universe from a stage to a living, breathing, four-dimensional entity, the arrow of time. Why does time only move forward? So far, we've explored the relativistic nature of time, its flexibility and dependence on motion and gravity. But one fundamental aspect of our experience of time remains largely unaddressed: its relentless, unidirectional flow. We remember the past, but we cannot change it. We anticipate the future, but we cannot know it with certainty. Why does time only move forward? This is known as the arrow of time. The laws of physics, at their most fundamental level, are largely time-symmetric. That is, if you were to watch a movie of most physical processes and then run it backward, the reversed movie would still obey the laws of physics. For instance, a ball rolling down a hill could, in principle, roll back up the hill according to Newton's laws if an external force pushed it. A gas expanding into a vacuum could, in principle, spontaneously recontract. Yet, in our everyday experience, these things never happen. Eggs don't spontaneously unscramble. Broken cups don't reassemble themselves. The universe seems to have a preferred direction for time. This unidirectional nature of time is predominantly explained by the second law of thermodynamics, which states that the entropy of a closed system can only increase or stay the same. It never decreases. Entropy is often described as a measure of disorder or randomness. Systems naturally tend towards a state of greater disorder. Imagine a meticulously organized room. Over time, without conscious effort, it tends to become messy. You don't see a messy room spontaneously organize itself. This is because there are far more ways for a room to be messy than for it to be tidy. Similarly, gas particles in a corner of a box will naturally spread out to fill the entire box, increasing the overall disorder, entropy, of the system. It's statistically overwhelmingly improbable for them to spontaneously gather back into the corner. The universe, as a whole, appears to be an expanding system, constantly increasing its entropy. From the Big Bang, a state of incredibly low entropy and high order, the universe has been evolving towards higher entropy states. This cosmic progression from order to disorder gives time its fundamental direction. The past is the state of lower entropy, and the future is the state of higher entropy. This explanation for the arrow of time is compelling because it aligns so well with our macroscopic experience. However, it still leaves some deeper questions unanswered. Why was the early universe in such an incredibly low entropy state to begin with? This is a question that pushes the boundaries of cosmology and statistical mechanics. Some theories propose that the Big Bang itself was an incredibly improbable fluctuation, or that our observable universe is just one pocket in a larger, more complex multiverse. Another perspective on the arrow of time comes from quantum mechanics and the process of measurement. In quantum mechanics, particles exist in a superposition of states until they are measured. The act of measurement collapses the wave function, forcing the particle into a definite state. This collapse is an irreversible process, contributing to the arrow of time at the quantum level. While the equations of quantum mechanics are time-symmetric, the act of observation introduces an inherent irreversibility. The psychological arrow of time also plays a role in our understanding. We remember the past and not the future. This is because our brains are designed to record and process information about events that have already occurred. Memory itself is an entropic process. The formation of memories involves changes in the brain's physical structure, increasing its internal entropy. We construct our understanding of the world by building narratives from past experiences, projecting them into what we call the future. Finally, there's the cosmological arrow of time linked to the expansion of the universe. As the universe expands, it cools and becomes less dense. This expansion provides a global direction for time. If the universe were to contract, some theories suggest that the arrow of time might reverse, with entropy decreasing and events unfolding backward. However, current observations strongly suggest that the universe's expansion is accelerating, making a future contraction scenario less likely. The arrow of time, therefore, appears to be a multifaceted phenomenon arising from thermodynamics, quantum mechanics, and even our own cognitive processes, all seemingly driven by the fundamental tendency of the universe towards greater disorder. It's a testament to the fact that even seemingly simple observations, like time moving forward, can lead to profound and complex scientific inquiries. Time at the quantum level, a blurred reality. As we delve deeper into the nature of time, we inevitably arrive at the realm of quantum mechanics, the theory that describes the universe at its smallest scales. And here, the neat, orderly picture of time we've built begins to blur and even dissolve in some interpretations. In the classical world, time is a continuous parameter. We can imagine measuring it with arbitrary precision. But at the quantum level, the very notion of a precise, continuous time becomes problematic. The Heisenberg uncertainty principle famously states that certain pairs of properties of a particle, such as its position and momentum, cannot both be known with arbitrary precision. There's a fundamental limit to how much we can know. This principle also applies to energy and time. Delta E, delta T is greater than or equal to where delta E is the uncertainty in energy. Delta T is the uncertainty in time. AH bar is the reduced Planck constant. This means that if we precisely measure the energy of a quantum system, we become highly uncertain about the duration for which it possessed that energy. Conversely, if we precisely measure a very short duration, the energy of the system becomes highly uncertain. This uncertainty suggests that time at the quantum scale might not be a continuous flow, but rather a granular or chunky phenomenon. Some physicists propose the existence of a Planck time TP, the smallest possible unit of time. It's derived from fundamental constants (TP equals C5 GG, approximately equals 5.391044 seconds, where g is the gravitational constant, c is the speed of light, a is the reduced Planck constant, below the Planck time. Our current understanding of physics breaks down. Spacetime itself is thought to become foamy or highly fluctuating, and the very concept of time as a smooth continuum may cease to apply. It's like trying to describe the individual atoms of water when you're looking at a river at that scale. The river as a continuous flow loses its meaning. Another perplexing aspect of time in quantum mechanics arises from the problem of time in quantum gravity. When physicists try to unify general relativity, which describes gravity and the large-scale structure of spacetime, with quantum mechanics, which describes the very small, they encounter a deep conceptual difficulty regarding time in many formulations of quantum gravity, such as the Wheeler-DeWitt equation. Time simply disappears from the fundamental equations. The universe appears to be static, frozen in an eternal now. This is known as the problem of time. This emergent time, perhaps time isn't a fundamental entity, but an emergent property that arises from the collective behavior of quantum components, similar to how temperature emerges from the motion of individual atoms. In this view, time is a statistical phenomenon, much like entropy. Many worlds interpretation. In this interpretation, every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. In this view, time might be seen as the unfolding of these different branches. Relational time, similar to Leibniz's view, time might only exist in relation to changes between physical degrees of freedom. If nothing changes, then there is no time. The problem of time in quantum gravity is one of the most profound, unresolved questions in physics. It suggests that our intuitive understanding of time as an ever-flowing river might be deeply flawed. When we probe the ultimate nature of reality, it challenges us to rethink whether time is a fundamental constituent of the universe or merely a useful tool for describing change within it. Perhaps time is not a stage upon which the universe acts, but rather an emergent property of the play itself, the beginning and end of time. Cosmology's grand narrative, our journey through time, would be incomplete without considering its cosmic narrative, its beginning and its potential end. Cosmology, the study of the universe as a whole, offers fascinating, if still speculative, insights into these grand questions. The prevailing cosmological model is the Big Bang theory. This theory posits that the universe began approximately 13.8 billion years ago from an extremely hot, dense state. Before the Big Bang, our current laws of physics break down. It's not just that we don't know what happened. It's that the very concepts of space and time, as we understand them, may not have existed. The Big Bang is often described as the beginning of spacetime rather than an explosion in space. It was the moment when spacetime itself began to expand. Therefore, asking what happened before the Big Bang might be like asking what is north of the North Pole. The question itself might be ill-posed if time truly began at that singularity. However, some theoretical frameworks attempt to peer before the Big Bang, cyclic universe models. These models propose that our universe is just one in an infinite series of universes, each undergoing a cycle of expansion and contraction, Big Bang and Big Crunch. In this scenario, time might be eternal, with our universe representing just one phase of a cosmic cycle. Multiverse theories. These theories suggest that our universe is just one of many, perhaps an infinite number of universes, each with its own laws of physics and its own trajectory through time. In some multiverse scenarios, time might be a local phenomenon, arising within individual universes, while a more fundamental multiverse time remains elusive. Quantum foam and pre-Big Bang scenarios. Some quantum gravity theories suggest that the Big Bang arose from a quantum fluctuation in a pre-existing quantum foam, where spacetime as we know it didn't exist in a coherent form. The future of time, according to cosmology, depends on the ultimate fate of the universe. Current observations suggest that the universe's expansion is accelerating, driven by a mysterious force called dark energy. If this acceleration continues indefinitely, the universe faces a scenario known as the Big Freeze or heat death. In the Big Freeze, the universe would continue to expand, cool, and dilute. Stars would eventually burn out, black holes would evaporate through Hawking radiation, and matter would decay. Eventually, the universe would become a vast, cold, empty expanse where all energy is uniformly distributed and no further work or processes can occur. Entropy would reach its maximum. In this scenario, while time would technically continue to flow, there would be no discernible events or changes to mark its passage. Other hypothetical scenarios for the end of the universe include the Big Crunch, if dark energy eventually reverses its effect, or if there isn't enough dark energy. Gravity could eventually halt the expansion and cause the universe to recollapse into a singularity, mirroring the Big Bang. In this case, time might reverse its arrow as the universe contracts and entropy decreases. The Big Rip, if dark energy continues to strengthen. In this dramatic end, the very fabric of spacetime would be ripped apart. These cosmological narratives, while speculative, underscore the profound connection between the fate of the universe and the nature of time. Whether time is finite or infinite, whether it has a beginning and an end, these questions push the boundaries of our scientific and philosophical understanding. They remind us that our human experience of time, while deeply personal, is also intimately tied to the grand cosmic drama unfolding around us. The philosophy of time, realism versus anti-realism. The scientific theories. Philosophers have grappled with the nature of time for millennia, often categorizing their views into two broad camps, realism and anti-realism. Time realism holds that time is a fundamental, objective feature of reality, existing independently of human consciousness or any events occurring within it. Though a nuanced form of realism can still accommodate relativistic effects. For a time realist, time would exist even if nothing were to change, or if there were no observers. It's a fundamental dimension or substratum of the universe. Arguments for time realism often point to our intuitive experience. We feel time passing, and this feeling is universal among humans. The predictive power of physics. Scientific theories, particularly those describing causality and motion, rely on time as a fundamental parameter. The existence of causal relationships. Events are linked in a temporal sequence, where causes precede effects. Within time realism, there are further distinctions. Presentism. Only the present moment is real. The past is no longer real, and the future is not yet real. This view resonates with our intuitive feeling of moving through time. Eternalism block. Universe. All moments in time, past, present, and future, are equally real. Spacetime is a four-dimensional block, and our experience of now is simply our conscious mind moving along a particular world line within this block. This view is often seen as more compatible with special and general relativity, where spacetime is treated as a unified whole and there is no privileged now. If time dilation and length contraction are real, and simultaneity is relative, then the idea of a universal now becomes problematic, lending support to the eternalist perspective. Time anti-realism or idealism argues that time is not a fundamental aspect of reality, but rather an emergent phenomenon, a mental construct, or a convenient way for us to organize and perceive change. In this view, time is not out there independently existing, but rather in here, in our minds, or in the relationships between events. Arguments for time. Equations don't include time, then it might not be fundamental. The relational view. If time is merely a measure of change, and if there were no change, there would be no time. This aligns with Leibniz's ideas, subjectivity of time perception. Our wildly variable experience of time suggests it's not a purely objective entity. The unobservability of bare time. We can only observe time through change or motion. We never observe time itself flowing. One famous philosophical thought experiment against time realism is that of a static universe. If the universe were completely unchanging, no motion, no events, no entropy increase, would time still pass? A time realist would say yes, it would continue to flow, even if we couldn't measure it. A time anti-realist would say no, if nothing is changing, then there is no time. The debate between realism and anti-realism highlights the profound challenges in defining something as seemingly fundamental as time. Is it a noun or a verb? Is it a thing that exists, or a process that occurs? The scientific discoveries of relativity and quantum mechanics have significantly fueled this philosophical discussion, pushing us to question deeply held assumptions about the nature of reality. The illusion of the present and the nature of memory. Our subjective experience is dominated by the present moment. We live in the now. The past is gone. The future is yet to come. But is this present truly a razor-thin slice of reality, or is it an illusion? From a purely physical perspective, particularly within the framework of eternalism, the concept of a unique, universal present is problematic. As we discussed with the relativity of simultaneity, what is now for me might be past or future for an observer in relative motion. This suggests that the present is not a fixed point in space-time, but rather a subjective perception tied to an observer's world line. Neuroscientists suggest that our present moment is not an instantaneous point, but rather a duration, a specious present. It's a small window of time, perhaps a few seconds long, that our brains actively construct to give us a coherent sense of continuity. This involves integrating sensory information, memory, and prediction into a unified experience of now. If this specious present is too short, our world would appear as a series of disconnected snapshots. If it were too long, we might struggle to react to rapid changes. The nature of memory also deeply shapes our perception of time. We build our understanding of the past through reconstruction, not exact re-experience. Memories are not like perfect recordings. They are dynamic, often re-edited and recontextualized each time we recall them. This reconstructive nature of memory means our past is a living, evolving narrative within our minds. This might explain why our perception of past events can shift over time, or why different individuals can have vastly different memories of the same event. The human brain's ability to create a sense of coherent narrative from discrete experiences, integrating past events into a perceived present, is a remarkable feat. It allows us to learn, plan, and build complex societies, but it also blurs the lines between objective reality and subjective construction when it comes to time. Consider the role of causality. We instinctively believe that causes precede effects. This fundamental principle underpins our understanding of the universe and our ability to predict future events. If the future is truly as real as the past, as in eternalism, then how do we reconcile this with our sense of free will and the idea that our actions can influence the future? This is a profound philosophical challenge. Some argue that free will operates within the constraints of the block universe. Our choices, though seemingly made in the present, are simply part of the pre-existing fabric of spacetime. Others propose that quantum indeterminacy provides a loophole for free will, suggesting that the future is genuinely open until quantum events are actualized. The very concept of flow also deserves attention. We often speak of time flowing like a river. But what does it flow through? If time is a dimension analogous to space, then saying it flows is like saying space flows. It's a metaphor that might be misleading. Perhaps it's not time that flows, but our consciousness that moves through time. Or perhaps the flow is merely the continuous process of events unfolding, driven by entropy, the illusion of the present, the reconstructive nature of memory, and the intricate dance between causality and free will all contribute to the profound mystery of our subjective experience of time. It's a reminder that even when physics describes the objective reality of spacetime, the human mind adds its own layers of complexity and interpretation. Is time an illusion? After traversing the scientific and philosophical landscapes of time, a provocative question lingers. Is time, in its entirety, an illusion? This isn't a new idea. Philosophers like J.M.E. McTaggart famously argued in the early 20th century that time is unreal, based on his analysis of the inconsistency of past, present, and future as absolute properties. Some contemporary physicists and philosophers, influenced by the problem of time in quantum gravity, similarly suggest that time might not be a fundamental aspect of reality. Carlo Rovelli, a prominent theoretical physicist working on loop quantum gravity, argues that time is an emergent property arising from the interactions of fundamental degrees of freedom. In his view, the world is not a collection of things, but a collection of events. Change is fundamental, and time is merely our way of organizing that change. He suggests that what we perceive as time is a consequence of the universe being in a constant state of flux, and our brain's capacity to register and order these changes. If time is an illusion, it is certainly a very persistent and compelling one. Our entire lives, our memories, our plans, our understanding of cause and effect are structured around the concept of time. To completely discard it would require a radical revaluation of reality. However, it's crucial to distinguish between different senses of illusion. Illusion as subjective experience. Our perception of time, with its varying speeds and emotional biases, is certainly subjective and could be seen as an illusion in the sense that it doesn't perfectly reflect an objective, uniform flow. Illusion as emergent property. If time is an emergent phenomenon arising from more fundamental, timeless interactions, it isn't an illusion in the sense of being unreal. Rather, it's a higher-level description that simplifies a more complex underlying reality. Just as temperature is an emergent property of the motion of atoms, but not an illusion, it's a real and useful concept. Illusion as fundamentally unreal. This is the most radical claim, suggesting that time does not exist in any objective sense whatsoever, and our experience of it is a fundamental misinterpretation of reality. The scientific consensus, at least for now, leans towards time being a fundamental aspect of reality, albeit a far more complex and relative one than Newton imagined. While some theories of quantum gravity hint at a timeless underlying reality, these theories are still under development and face significant challenges. Even if time is emergent, the fact that it emerges so consistently and universally for all observers when corrected for relativistic effects suggests it's a very robust illusion, if it is one at all. It's an illusion that allows for the very existence of processes, change, and ultimately consciousness. Perhaps the better way to frame the question is not whether time is real or an illusion, but rather, what is the most fundamental description of time? Is it a bedrock dimension, or is it a derivative concept, a shadow cast by something even deeper? The ongoing quest to reconcile general relativity and quantum mechanics, to develop a theory of quantum gravity, is where the ultimate answer to what is time, really, may lie. Until then, we continue to experience it, measure it, and marvel at its profound mysteries. We live in a universe where the past informs the present, where the present shapes the future, and where every tick of the clock, whether perceived as fast or slow, is a whisper of the universe's grand, unfolding narrative. And as you finish these words, wherever you are a part of that narrative, moving forward, one precious moment at a time. The clock continues to tick, and the questions continue to beckon. Perhaps the real answer is not a single definition, but the very act of continually seeking to understand it. What is time, really? The journey of asking the question itself might be the most profound part of the answer.